Hello everybody, this video is going to be about instantaneous rates and rate laws. We're going to start with the instantaneous rates. So last time we learned about average rates. The average rate was telling us the speed of a reaction between two specific time points. It could have been starting and ending, or it could have been between minute 5 and minute 10, could have been between any two specific points. But it doesn't tell us the rate at the exact moment in time. So an instantaneous rate is what we use to figure out an exact rate at an exact time. To do this, we're going to use a graph. So let's use this equation here. If we plot the concentration over time, if we look here, this is of one of our reactants. So we're plotting the concentration of a reactant as time is going on. If you can look here, you see how the slope is steeper here, and then the slope gets shallower as we go on. So you can see that the rate is not the same at every point in time. So if we took that slope of a tangent line to a specific data point on this curve, that would be our instantaneous rate at that exact moment in time. Remember that a tangent line is a straight line that just touches the curve at that exact one point. And what you have to remember is that our slope is rise over run. And when you draw your tangent line, you need to be very careful. You need to make sure that the angle on one side between the line and the tangent matches the angle on the other side. Now in a fancy graphing calculator, if you had data to type in, you can make the calculator do it for you. But if you just have a graph on a piece of paper, right, you're going to have to draw that tangent line. Use a ruler, okay? Spend some time, be careful with what you're drawing, make sure those angles match, right? So you get the right line, the right slope. One of the things we should think about is, why is the slope getting shallower as we go on? Why is it slowing down? Why does the rate get slower as we proceed? And that's because the reactant concentration is decreasing as those reactants get used up. And if you remember from a previous lesson, the rate is dependent upon concentration. The molecules have to collide to react. And if there's not enough reactants around, it's going to take longer and longer for them to find each other and collide with each other. If you're really concentrated, they're going to bump into each other very often, and the rate will be very fast. Well, as your concentration decreases, there's not as many molecules to collide with, right? We're going to have a slower rate. It takes longer for them to find each other to collide with. So you can see here, that's that really fast speed, and down here is the slower speed. Okay. So for our practice problem, you should have a graph to glue in your notebook. You're going to draw that tangent line. People really struggle with this. I think it's not as common in math classes these days to do these tangent lines. And so I think people haven't gotten the practice they used to. So let's give it a try. Use pencil, right? If you got to erase it, right, no big deal. So what is the instantaneous rate at 30 seconds for the decomposition of hydrogen peroxide? Here is your graph. You're going to find 30 seconds. Right here, that's the data point that you want. You're going to draw a tangent line to this point. Once you have your tangent line drawn and your angles are equal on both sides, then we find the rate by finding the slope of that line. So pause the video for a minute and try to draw your tangent line. Let's see how that went. So I did my best to eyeball it. Now try to find that slope. So what you want to do to make your life easier is we will often extrapolate this line and make sure we draw it long enough that we can get to some data points that are a little bit more obvious and not as estimated. If you can get to an exact amount, right, to one of your little, line markings, it makes things a little bit easier. Is it very, very likely we're all going to get slightly different answers? Yes. On a question like this, if you have drawn a decent tangent line that shows that you understand it should be equal on both sides, you made a good faith effort to do that, you have a reasonable line, good calculation with your line, you would get the points. Or we would set it up in a way where perhaps we draw the tangent line already, and then you just have to do the slope calculation part. So it would be pretty straightforward on a quiz. There wouldn't be any worry about, oh, my answer was slightly different than yours. Is that going to matter? I would set it up in a way that it didn't matter. So now we have our line. And I'm just estimating the best that I can. Rise over run. And I give my answer. Now, if you notice, my answer is negative, right? Because this is a negative slope. We do final minus initial. Now, if you used different data points, the work portion will look a little different. You may not have gone between 10 and 50 seconds to get your run, right? That's fine. Your final answer should come out the same because the slope of this line is the same everywhere. So it shouldn't matter which data points you use to get your rise over run from your tangent line. We should get the same answer when we're done. Right, there's our rise, there's our run. All right, next is going to be rate laws. We use rate laws a lot. It's one of the ways we can calculate the rate of a reaction using the concentration. So a rate law is just an equation that we use. It's going to relate the speed of the reaction to the concentrations of the reactants. So I'm going to give you a generic equation so that we can see in a generic rate law. The lowercase a's and b's and c's and d's are the coefficients. The capitals are our chemicals. This would be the rate law. The rate of the reaction equals K times the first reactant raised to an exponent times the concentration of the second reactant raised to an exponent. Notice that only the reactants are used. We do not include the products. The products are not participating in the reaction occurring. They are not colliding to make this happen, right? It's the reactants that need to collide for the rate to happen. So it's only the reactants that we care about. Now, if you notice, these exponents are not the coefficients, are they? This is an x and this is a y. That's just different random numbers that are going to go in there. The exponents are going to tell us something. They're telling us what's called the order of reaction with respect to that chemical. Okay? So what does that even mean? What's an order? So an order is the mathematical effect of the concentration on the overall rate. It's basically us expressing mathematically how much does the rate change when we change the concentration? Does the rate double? Does the rate triple, etc.? Sometimes people don't know how we literally say the orders out loud. It sounds a little bit funny. So I'll show you kind of how we talk about it. So we say the reaction would be xth order with respect to A. So I would say something like it's first order, or it's second order, or it's third order. Same with Y. So it's second order with respect to A. It's first order with respect to B. If I want to talk about the overall order of the entire reaction, I add those exponents together. So it would, if the X was 1 and Y was 2, the overall order would be third. The next question is, what is this K thing? Okay, the K over here is the rate constant. It's a numerical value that's going to relate the reaction rate and the concentrations at a very specific temperature. It only works for individual temperatures. If you change the temperature, you need a new rate constant. And it's going to be different for every reaction. It's different at every temperature. And it's basically, once again, one of those correction values. Correction values occur because we don't have perfect combinations of units where everything magically works out. So our correction values fix that for us, right? So if you have a very large K value, that means the reaction is going to happen very, very quickly. If you have a small K value, it means it's going to go slowly. Okay. Sometimes we're calculating the exponents, the orders. Sometimes we're calculating the K value. Sometimes we're calculating the rate if you're given this other information. So we're kind of sometimes solving for any variety of these things. So one thing that's really, really, really important to understand is that rate laws are always, always, always determined experimentally. We literally react the chemicals, we measure their their concentrations as time goes by, and we mathematically derive and figure out what the rate law would be based on our data from our experiment. They're always in terms of the reactants, not the products. And it's important to notice, here's an equation here. Here's its rate law. You should notice, okay, there's a coefficient of 1 here. There's a coefficient of 2 here. But if you look at the rate law, there isn't a 2, right? The coefficient here is a 1, the exponent here is a 1. So the exponents, our orders, are not coming from our balanced equation. What these are actually coming from is the rate determining step of the reaction. So remember that reactions can happen in different steps. Sometimes it's a single step, sometimes it's 2 steps, 3 steps. And so what determines the overall rate of the reaction is the slow step. The slow steps coefficients tell you what the exponents are. So in the slowest step of this reaction, one of these fluorine molecules needs to collide with one of these. That's what's happening in the rate determining step. Not the overall reaction, but in the slowest part of the reaction. So just be a little bit careful that you don't just grab these coefficients. It's not that simple. Now, if you're told it was a single step reaction, then they should match. If you're told what the rate determining step is, you can use those coefficients. But we just don't often know that information, right? So we do have to determine it experimentally. So how do we determine it? Well, you're going to write out your skeleton rate law with just, rate equals K, and then your concentrations, but we are looking for the exponents. You look at your data, which is almost always given to you in a chart. Then what you're going to do is you're going to try to look at the data and find some patterns. You're going to try to find two trials where one of your reactants concentrations is held constant. It's not changing. And then we can look at how the other substance is being changed. So we can't change everything at once. We're going to hold one reactant concentration constant. We're going to change the other. And when we change the other one, we're going to see how the rate changes. We're going to try to see, does my rate double? Does my rate triple? Does my rate quadruple? Does my rate get cut in half? Does it go slower? So those are the things that we're going to be looking for. So let's do a practice one. Here's our equation at the top, and here's some rate data that we have. Here's my skeleton rate law. Rate equals my rate constant times my concentrations of my reactants from up here, but I have an X and a Y because I don't know what order they are yet. Now I'm going to come over here and look at the chart. I need to hold something constant. Let's look at trials number 1 and trial number 3. If you look at trial number 1 and trial number 3, you should notice, hey look, my ClO2 is staying the same. And what did I do here? I doubled my concentration of my fluorine gas, right? So one of them is being held constant and one of them doubles. Next, let's look at how that affected the rate. When I doubled this reactant, do you see that my rate doubled? Sometimes it's easy for us to notice that it's double, right? Sometimes you need to punch it in your calculator, right? People sometimes have a hard time seeing if it's a triple or a quadruple, right? So you can punch it in your calculator to see. What you see right here, where I tell you which trials to use, what stays constant, how something else changes, and how the rate changes, is required information to show on your paper. This counts as showing work, okay? You got to tell me which trial you're using. You have to tell me what's being held constant. You have to tell me how the other one changes. You have to tell me how the rate changes. If you don't show that, you don't get credit. And that's not just me. Like in AP Chem, the graders for the AP test don't give credit if you don't tell them this information. You can't just magically come up with your orders. You need to justify them. Okay. So now what we have to do is figure out what the exponent would be that would mathematically result in that change. That's what we're looking for. What am I mathematically going to do with that exponent to get that change that I'm seeing? So back to the same question. Here's my skeleton equation. Well, the rate doubled, right? So you're going to put a 2 for your rate doubling. Now, your concentration of fluorine gas doubled. So you're going to put a 2 there. You held this one constant, right? If it's constant and it's not changing, we don't need it there. K is a constant, so get rid of that. We don't care about it. Now what we're doing is we're comparing this. When I doubled my concentration, my rate doubled. So which exponent do I need for this to turn out to be a true statement? Well, it's a 1. So the order with respect to F2 is a 1 up here. X equals 1. You do not need to show me all these steps in between. You do need to show me this last part. Now, if the rate had tripled, you'd put a 3 here. If it had quadrupled, you'd put a 4 here. If it had been cut in half, you would put a 1/2, right? So this part down here we should see on our paper as well. Now, one last thing we have to do is we need to go back and do this all over for the other reactant. You can't just forget that there was more than one chemical there, right? So back here, but this time, look, I'm using trials 1 and 2. F2 is held constant. What happened to the ClO2 concentration? This time we quadrupled it. And now look at what happens to your rate. Going from 1.2 times 10 to the minus 3 to 4.8 times 10 to the minus 3, that's also a quadruple, isn't it? So quadrupled, so I put a 4. My concentration quadrupled, so I put a 4. I'm getting rid of all those constants. So I'm looking to see what exponent makes that a true statement. Well, a 1. It's first order with respect to this as well, which if you remember from a few slides ago is what we saw. So now, if you're going to finish the problem, we need to put all this information into the rate law. You need to put your exponents in where they belong. You do not have to put a 1, okay? You could leave it off just like in math class, but it is very common to put it there. So I would never take points off. You can have negative orders. Things can slow down. You could have a 0 order where it doesn't participate in the slow step, so that reactant is not going to show up in the rate law. You could have what we call fractional orders. We usually don't do those very often, right? It's usually whole numbers and they're usually pretty small. 0, 1, 2, 3, 4, right? If you think about it, it would be pretty low statistical probability to have a chemical reaction that occurs if you have to have 4, 5, 6, 7 molecules collide with each other just right. That's really low odds of happening, right? Having, 2 things collide, sure. Having 3 things, yeah, that can happen, right? But the bigger and bigger your exponents get, the less likely it is to really happen. So the nice thing is we usually don't see crazy numbers for these exponents. All right, let's do another one. We want to know what's the order with respect to A. So I'm going to look here. Okay, I want to find A, which means B is going to have to be held constant. Which trials hold B constant? Well, look, trials 2 and 3. So what's happening to A during trials 2 and 3? Okay, well, A is doubling, but that's weird. The rate doesn't change. So what does that tell us? That means my exponent must be a 0 because there's no change here, right? Nothing's happening. That means that A, chemical A, whatever that happens to be, does not participate in the rate determining slow step. It still needs to be there for the reaction to happen. It's still going to end up part of the overall reaction, but it's not what's slowing the reaction down. It's not determining the rate. Now let's do B. What's the order with respect to B? So now we need to hold A constant. All right, let's see. Trials 1 and 2, A is held constant. Well, let's see. Okay, I doubled B, and what happened to my rate? I went from 1.25 to 2.5. Okay, that's like a double, right? So if my rate doubles when my concentration doubles, that means my exponent must be a 1. If I ask you what the overall order of the reaction is, you're going to add these together. So it's a 1. Now I'm going to ask you what's the rate law. Well, if A is raised to the 0 power, that's just a 1, right? So it kind of just goes away. I don't need to put it into my rate law. So my rate law is going to be K times the concentration of B raised to the first power. All right, let's try another one. Why don't you pause the video and see if you can figure out the questions on the screen. I'd like you to find the order with respect to the chlorine. I'd like you to find the order with respect to the nitrogen monoxide, what the overall order is when you add up those exponents, and then tell me what it would look like when you plug everything into the final rate law. You can go ahead and pause the video and give that a try. All right. So to find the chlorine, I need to hold the nitrogen monoxide constant. So that'll be trials 1 and 2. We always say trial 1 is the first one in the line. So if it doesn't literally say trial 1, you just can put a 1, 2, and a 3. You just label the rows. So trials 1 and 2, that's held constant. Oh look, this doubles and this doubles. So that's a 1 exponent. For nitrogen monoxide, we got to hold the chlorine constant. So let's do trials 2 and 3. This doubled. What happened to your rate? What change is happening here? If you were to divide these in your calculator, you'd find out that that's quadrupled, right? So what exponent do I have to raise a 2 to get a 4? 2 to the what gives me 4? 2 to the 2. That's like the hardest sentence to say. It sounds crazy. You have to raise a 2 to the 2 power to get a 4. So the overall order of the reaction is 3. 3 things are going to collide in the slow step to make this reaction rate determined. There we go. All right, on the next one, I'm going to add something. Okay, I'm going to add another thing that we could potentially do. So here's your data chart. I'm asking for the rate law, but I'm also asking for the rate constant. So what we're going to do is we're going to find the rate law first, okay? You have to figure out what your equation is. Then we can plug some data into the equation and calculate what K must be. So here's my skeleton equation. Pause the video, take a moment, and try to calculate and figure out what your exponents would be. Try to get to the point where you have your rate law written out. All right, so if I look at trials 1 and 2, this is held constant, so the iodide is changing. Okay. When I look at that and compare that rate, it's doubled, isn't it? I doubled this and this doubled. Sometimes people are bothered by the fact that trial 2 was not higher concentration than trial 1. It doesn't matter. If I go from experiment 2 to experiment 1, that's a doubling, right? Now for the next one, let's look at experiments 2 and 3. This time this doubled, and this also doubled. So, oops, those animations are out of order. There we go. So there's my rate law. Now what I'm going to do to solve for K is I'm going to rearrange, plug everything in, and solve for it. You can pick any trial's data. It doesn't matter. Pick any of them. They will all give you the same information. K is the same, right? Because we're not changing the temperature, K is not going to change. So if I use experiment 1 to plug in, or experiment 2, or experiment 3, I will get the same K value no matter what. I'm just going to use the first one on the chart. I'm just going to use line 1. The rate gets plugged in. My concentrations get plugged in. I calculate that out. Now, the units on the rate constant people really care about, okay? Sometimes the entire question is only asking what are the units on the rate constant. So if you look, we have a molarity per second on the top, and we have 2 molarities on the bottom, don't we? Okay, one of those molarities will cancel. If the seconds is on the denominator up here, it's going to flip down here, right? So we're going to end up with units of molarity per second on the bottom. So my rate constant is 0.08 molarities per second, but that's on the bottom. You could also use a -1 exponent instead of putting them as a fraction. It doesn't matter. There's a handout in your reference sheet where I kind of walk you through the variety of ways the units cancel to show you a variety of units that you might get on your rate constant. Because remember, the rate constant is our correction value. It's what's fixing everything for us, so it'll be different based on the exact rate law that you have. Now, sometimes your data tables are a lot bigger, so it can be a little bit harder to figure out which trials to use. They're not always right next to each other. Sometimes there's lots of trials you're not even going to look at. So you have to just kind of be on the hunt for your patterns, right? You're really looking for those patterns. The other thing that can be tricky is that sometimes they may not give you the trial combinations that you really want, that you really need, where something is never going to be held constant. So what you would do is you would determine all of the exponents you can, just the way we did. And then the one where you can't figure it out using the patterns, you would just plug information in and try to solve for it that way. All right. Now, last slide I have is because this always gets asked over and over. So I'm hoping making it an actual slide in the PowerPoint will be helpful. What counts as showing my work? Because these are a little bit of a weird problem. There is math involved, but a lot of it's mental math. So what exactly, how do I show a pattern? What am I looking for? This is showing you exactly what you need. You do not have to put it in chart format, okay? But I do need to see this type of information. What trial's being used, what's being held constant, what is changing, how is it changing, what's the factor that the rate is changed by, and then what does that imply about the order, okay? If you're trying to figure out, is it double, is it triple, punching in your calculator, personally for me in my class, I'm not going to ask you to show that part to me. Some teachers, maybe they do. I don't, okay? These are problems that get a lot easier once you've done a couple of them. They will become pretty robotic. You're just finding your trials and figuring out double, triple, that kind of thing. You will have some that get thrown at you that are a little more unique, right? So some of them in the homework or good practice, trying to make you think and stretch your brains just a little bit. Okay, but the same principle is always going to apply. You're looking to see how the concentration changes the speed of the reaction. All right. Okay, that's it, everybody. I hope that was helpful. Bye.